To the naked eye, this sentence looks like a standard harmless greeting. It renders perfectly on your screen, but this text is actually a container. It is carrying a hidden payload, a secret password of some sort, that is completely invisible to the human observer, and it is nested directly in between the letters. This is the next logical step in my exploration of steganography. We have previously looked at images where we could tweak the color values to hide data in those changes. We have also looked at audio where we could hide secrets in the sound waves. But text presents a different kind of a problem. In an image, if you change a pixel's color value by 1%, nobody notices. But text is completely different. An A is an A. You cannot slightly darken a letter without changing the font or raising suspicion. So how do we hide data in a medium that appears to have absolutely no room for manipulation? To solve this, we have to stop looking at the screen and look at the database behind it, the Unicode library. To a computer, text isn't shapes, it's a lookup table. Unicode is the universal standard that assigns a unique ID number to every character in human history. But buried deep within this library, alongside the alphabets and emojis, are characters designed to be invisible. They are called zero-width characters. They exist strictly for formatting. They tell the computer how to break lines or how to fuse characters together. They have no width, no shape, and no visual footprint. Now, for this experiment, I am repurposing 3 of these specific formatting tools to create a hidden binary language. Now, to understand the hack, you have to understand the original purpose. First is the zero-width space. In legitimate web design, this acts like an invisible perforation. Imagine a massive unbroken word, or a URL that is too long for a text box. This character is inserted to tell the computer, if you run out of room, you are allowed to break the line right here. It is a silent permission slip. For our purposes, we are assigning this the value of binary 0. Second is the zero-width non-joiner. This is a typography tool used to prevent characters from touching. In many fonts, letters like F and I will naturally merge into a single shape called a ligature to look aesthetically pleasing. This character acts as an invisible glass wall between them, forcing the computer to display them as separate entities. We are assigning this the value of binary 1. Third is the zero-width joiner. This functions as a digital glue. It is the engine behind modern emojis. When you see a male technologist emoji, the computer is actually rendering a man emoji and a computer emoji fused together by this invisible joiner. We will use this character as our flag, a bookend place at the start and the stop of our data stream so the decoder knows exactly where to look. I wrote a Python program to automate this process. It takes our secret message, let's say the word is secret, and converts it into raw binary data. It then translates that string of ones and zeros into a stream of these invisible characters. Finally, it injects that invisible stream into the middle of a standard cover sentence. Because the characters have a width of 0, the visible letters around them don't move. The sentence collapses around the secret, leaving no visual gap. Visually, the result is flawless, but just like with the image steganography, there is a digital anomaly. When we looked at the file properties before, we found a massive discrepancy in the image that we changed. In computer code, a single standard letter is 8 bits. That is 8 ones and zeros. Since we are translating every single bit into its own invisible Unicode character, we are bound by a strict 8:1 ratio. Let's look at the math. To hide the word secret, which is only 6 letters, we multiply 6 by 8. That gives us 48. This means to hide that one small word, we have to inject 48 invisible characters into the text. This creates a massive footprint. I tried to paste a short hidden paragraph inside a tweet. Visually, the text box looked almost empty, but the platform rejected it immediately. The character counter was in the negative thousands. Even though our eyes can't see the characters, the system actually counts them. This was just a fun experiment that exposes a fundamental disconnect in how we perceive the digital world. To us, text is static, a final product meant to be read. But to the machine, text is fluid, a deep ocean of potential codes and formatting instructions that we are completely blind to. By hijacking these invisible mechanics, we aren't just hiding a message. We are proving that our digital environments have layers that human senses simply cannot penetrate. We assume that if we can see it, we understand it. But as we have just seen, the most secure hiding place isn't in the shadows. It is right there, staring you in the face, hiding in the one place you would never think to look: the empty space. Thanks for watching. See you in the next one.